I didn't see it. Okay. You said $1 million.
Good morning, everyone. Morning. I'm Clem McKown. You can see it from there. Good. I'm Clem McKown from Team 1640 Sabotage. I'm going to talk about Swerve Drive this morning, and we've done Swerve for a long time. We have a lot of experience, and we've managed to find a lot of the wrong ways to do things. So we're going to talk about that. I'll have a presentation, and then between me and our other mentor, Gary Deaver, Gary, we can answer any questions you have about Swerve. So we will start. Very quick, what is Swerve when we talk about Swerve? Swerve is really a drivetrain in which all the wheels are independently driven and steered. Usually that's 4 wheels, but it doesn't have to be. It utilizes traditional wheels. The wheels are not McKown wheels, they're not Omni wheels, they're traditional wheels with good traction. And it's a holonomic drivetrain, which means we move in all directions. It allows the robot to move in any direction and independently translate its chassis orientation while you're moving. So the direction of motion and the orientation of the chassis are completely divorced from each other. We started Swerve as a summer project back in 2009. And one reason that we did so is because 2009's game actually was a good game for Swerve if you had it. We didn't have it, and we knew we couldn't develop it during the build season. But we recognized that for that year's game, which was everyone's favorite, Lunacy, everyone who was actually around during Lunacy is dead now. Because otherwise it'd be groans. But we started it as a summer project because we recognized that it was useful technology. We actually had a successful summer project. We had our first Swerve Drive robot in 2010. That's a picture of it on the side, or a CAD rendering. It's really different than what we have now, but that's where we started. And we've used Swerve every year except for 2016. And why didn't we use Swerve in 2016? Because it was just not a good game for it. That was Stronghold, and you had the barriers to go through and over and under. It was just not a Swerve game. Not that that kept everyone from using Swerve. We've made some key changes during the time. We went from having a Swerve module that was bolted to the frame, riveted to the frame, in fact, in the first year. We made them modules in 2011 because we realized that fixing a Swerve module, if it's bolted to the chassis, is going to take a long time and you'll miss games. We switched to, got identical modules rather than lefties and righties in 2012. Dynamic driving in 2013 so that we could change the chassis orientation as we were driving without changing direction. CVT in 2017, also field centric driving in 2018, and I'm adding drive straight Swerve because driving straight in Swerve was actually a trick we had to learn how to do. Swerve is great for maneuverability, and then you want to drive it straight and it's hard. Someone asked us why we did this, and that caused a little bit of soul searching. And the real reason why we did this is because in 2008, frankly, we sucked. We were terrible. We were We worked really hard to build really bad robots and didn't really enjoy it very much. And we needed a cultural change. So that year, we started doing summer projects. We had been just a school year team at that time. I became the head mentor in 2008, sort of by accident. But no one was really happy with where we were. We made a really terrible robot in 2008. So we started doing summer projects just to learn so that we could become a little bit competent in what we were doing. And we studied and tested the drivetrains because in our experience, we saw that robots that could move perform better in competition than robots that couldn't move and maneuver. It's true. I mean, if you look around, robots that move have the edge. And that helped in 2008. So we did this again in 2009. We said, we're going to do another summer project. We're going to do something more challenging. We picked Swerve Drive for a summer project in 2009 because first, it really had some key and very attractive technical advantages that we wanted to be able to use. So that was the technical reason for doing it. But also, it was going to be very difficult. We're not as bad in 2009 as in 2008, but we were still not really a competent team. And in fact, it was going to be impossible to do Swerve unless we made fundamental changes in how we ran the team. In the team's attitude about design, about building, planning, training, and really everything else. We could not be the team we were in 2008 and do Swerve. It wasn't going to happen. So part of the reason we did it was as a catalyst for cultural change on the team. Drilling a hole for a bolt and getting it within half an inch of where you wanted it was no longer going to be good enough. In terms of the technical benefits that we were looking for, the key thing, everyone thinks Swerve, it's really very agile, really 2D dimensional drive, drive in any direction divorced from chassis orientation, and it has normal traction. You're not getting rid of if you're using McKown's, you tend to get pushed around. If you use Omni wheels for holometric drive, you tend to get pushed around. You can't go up ramps. Swerve has normal traction. It also has some tactical stealth because I don't need to telegraph where I'm going by turning the chassis in the direction I want to go in. I can go in any direction regardless of what the chassis is pointing. Also, you stop even thinking about doing things like turrets or turntables for scoring devices once you have Swerve. It's really easy to turn the chassis. You don't need a separate turntable. Your scoring devices can be fixed on the chassis in terms of angular orientation. You can have you can program drive modes that are specific for games. In 2010, for example, you had that soccer ball that you were going to kick. One of the drive modes we had would simply drive the robot around stationary soccer ball so that you could maintain your kicking location and change your angle independently without moving the ball. Can't do that with other drive systems. That's really easy to do with Swerve. When you're being defended against, it's easy to set up the robot so that you can just hit the robot and then roll around them and continue on your path. Makes it a little harder to block a Swerve drive because you can do that. And you can roll left, you can roll right, a little bit like a football player. Another key point, there's not a lot of steering hysteresis in Swerve. If you're using normal tank drive, you have to overcome the static friction before you can start to turn. Swerve guide really don't have that so much. You're using steering to get over that rather than having to slide wheels sideways. One thing we found is that's really nice is it's compatible with field-centric driving. And field-centric driving, normally when we drive, it's robot-centric. You press the joystick forward, the robot goes forward. You turn it to the left and right to steer left and right. You pull the joystick back, the robot comes back. But with field-centric driving, our driver can push the joystick forward, and the robot goes downfield away from the driver, away from the steering station. Turn left, it goes across the field to the left. Right goes across the field to the right. You can pull it back. It doesn't matter what the orientation of the chassis is. So you can drive behind things that you can't necessarily see by simply following what you know, where the open path is on the field. You don't really necessarily need to see this. This was useful in the steampunk game. Steamworks. Because you had that stupid airship. Our drivers could drive behind the airship because they're going sideways. That's the way the field was oriented. And it's also, it's real nice because the serviceability is pretty high because the pivots can be set up on modules. It takes about 3 minutes to pull a module off of the chassis. You can another 3 minutes to put a replacement on. We set them up so that they're all pre-calibrated and all calibrated identically. So all you need is one spare. You can put it anywhere. It's already ready to work, and in about 6 minutes, you've replaced the broken element of your drivetrain with a working one, and you can go out to your match. No more missed matches because of drivetrain problems. They're drawbacks because that's the way life is. It's really complex compared to a traditional drive. It's not easy to execute. Now, when originally we did this, there weren't any COTS systems available. And the good thing is that there are good COTS systems that reduce the barrier to entry. So it's not as complex as it used to be, but it's still a complex system as compared to tank drive. The control software is really in a different world than tank. So even if you get the mechanical system right, you still have to deal with the software. Software for Swerve is complicated. Steering backlash needs to be managed. We talked about the driving straight problem. Our early Swerve drives did not drive straight. Really couldn't drive straight. Shifting is complex in Swerve because you have 4 modules. So everyone needs to have its own shifter. That's a lot of shifters. Weight's an issue. You don't want to have you don't want to add weight to your drivetrain. The mass on our original Swerve drive, our first one, it was 40 pounds. It was 10 pounds per module. We've gotten that down to just under 27 pounds now, and hope to get that down to about 25 pounds next year. Yes?
Is that the full chassis or just the modules itself?
Modules itself, not the full chassis. Motors, everything from the motor to the wheel. The cost is relatively high. It costs us about $1,200 for materials and parts to put together a system. Motor budget, you need to take that into account. You're going to use, if you have 4 wheels with Swerve, you're going to have 8 motors, and you need to start looking at your power distribution module and saying, well, how many slots do I have for other stuff that I need to do all my scoring and everything else. And driver training. Driver training on Swerve is not optional. It's gotten a lot better since we went to Field Centric. It was really intensive when we were doing robot-centric Swerve. Field Centric's easier. It still requires a lot of driver training. And one of the issues with our own devices that they're tall, they fit in the corners. That's a place where we might want to use for scoring devices, and we sort of fill up that corner space on the robot with Swerve modules. A little bit about the development history. When we started as this in a summer project, we actually started with VEX parts. We put together a VEX Swerve robot. That's just crazy, but we did it. But while we put together the VEX robot, we also worked out all of the math behind how to control a Swerve. If you're going to do the control, what do the angles need to be? What do the speeds need to be of the different wheels as you're maneuvering that Swerve through its paces? We actually put together a series of white papers on Swerve control, and those are available both on they're in Chief Delphi and on our own website. And at the end of the summer, we're at a point where we could start working on the design. How would we make a FRC Swerve module? And one thing we said we wanted to do, and we did, is that we wanted the wheels to be able to rotate infinitely. We didn't want wires that were going to say, well, you can rotate it 360 degrees, but you can't go past a certain point because otherwise you're going to break your wires. You need to turn it the other way. So we wanted it to be something that could rotate infinitely without any concern for wires. We actually went through, it says I went back and counted. We did 6 major designs during the autumn of 2009. And we would go through a design, we'd have design reviews. People would say, I don't like this, don't like that. We'd go back to the drawing board, redesign it, come back. We did that 6 times. We finally ended up with something that we were ready to prototype by December. And then we built the prototype, we tested it, made some more changes. But we were ready to actually implement Swerve Drive then in 2010. Every year though, after we go through our season, we'll go back and critique it again. We'll say, okay, what did we learn over the past year that we need to do better this year? What do we need to do better? What do we need to improve? What can we do in terms of reducing cost or improving reliability? We prototyped again when we did CVT for the first time. That was, we took an old module, we added CVT to it. CVT is continuously variable transmission. That's how we figured out how to make these shiftable, not by putting a typical gear shift where we would shift, say, with a dog shifter or a ball shifter from one gear ratio to another. We actually found some continuously variable transmission pulleys in which we could change the effective diameter of that pulley on the fly, anywhere between over a range of 2x diameter. And that turned out to be actually it's a lightweight way of adding gear shifting to these modules, and it made it practical to make a shifting module, because we didn't have the weight that, we didn't want to add another pound to each of these modules by putting in a gear shift mechanism. This way we have a pulley, which is a CVT pulley. We have a servo, which controls the gear ratio, and it really didn't add a lot of weight to do that. It did add some more programming though, because you now need to know what gear ratio you want at any given time. There's always complexity. We have a new design in the works, which I was planning to bring, and unfortunately I wasn't able to, because I just had some medical issues this week. But we're prototyping a system for next year. We think we can take a ½ pound out of each module, and it's a low profile module, so we're not having a tower in each corner of the robot anymore. It's also contains CVT, so it'll have all of the features of the old robot, but it'll be lighter, it'll be lower. We think it's going to be awesome, but time will tell. What we've done though is we've built 4 prototypes. We have that on a chassis now, and we're testing it to see how it works. We'll let people know. Every year, as we've gone through the Swerve process, what we've done is we do what we call value engineering. We try to, this is very evolutionary rather than revolutionary. We look for small changes we can make. If you look at a lot of these things on the side, we have changes that improve reliability or serviceability. We have changes that improve utility. They make the Swerve work better. And we have changes that improve manufacturability. Can we make this easier than we did before? Every year we try to make some improvements on the system, and also we track weight, we track cost, and it's just it's a way of documenting how we can make this better year after year. What features can we add? What reliability improvements can we make? The original ones is sort of a history here. We started working on the reliability because it needed work. Ultimately, we changed to changes that improve the utility and manufacturability. Just how do we make it easier? How do we make it cheaper? We try to do this on all of our things that we use year after year. Swerve works best for us because we use it almost every year, so it's something that it's a technology suite that we can work on and improve year after year, just make it better. Tools, we use SolidWorks for CAD. Everything gets CAD'd before it gets made. We also, and we didn't really appreciate it as a tool so much, but we have a wiki which really contains all of our design information, all of the test results that we run, and all of our robots designs year after year. And what we found is that this really helps the team from the standpoint of retaining institutional knowledge. When we do something in 2013, people can look in 2019 and say, what do we do? What have we faced this problem before? I think so, but I don't remember how we solved it. Well, we have a way of really going back, basically a team history book, to go back and see how we solved that. And our wiki contains a huge amount of content, most of which nobody cares about. But when you do need to understand how you solve problems in the past, how you've gotten to where you are today, it does provide really a guidebook to that. We've been sensitive because students are with a team for 4 years maximum. Mentors sometimes longer, but not infinitely. They're volunteers. You can't lock them up in a room and keep them on the team. Mentors move on as well. So how does a team retain institutional knowledge? We use our wiki to do that. And it's really proved very valuable. One problem we've solved recently is the whole issue of driving straight. And we analyzed why we couldn't drive straight, and we realized that the key issue is that the steering system had a lot of backlash in it. We were using a Bainspot transmission. That has backlash, particularly because you've got a double D connection between the drive shaft and the final planet carrier. That could start the season pretty good, but by the end of the season it was sloppy. It just didn't hold up very well. But what we did is we measured the backlash, and we measured the backlash from all the sources in that steering drivetrain. We quantified it, and we saw where the biggest problems were. And the key thing we found was that a lot of it was because of the Bainbot P60s. They were sloppy, and what we were able to find is we went and found a stepper motor with a gearbox in China, and it was a very high precision gearbox. It was made for doing things like 3D printing. We bought that. The first year we pulled off the stepper motors and throw them out and put our own motors on. After that we found out how to buy gearboxes without having to buy stepper motors that we had to throw out. We also saw that we still had some sloppiness in our own manufacturing as well. We would cut keyways too large and then have a little bit of slop on any rotation that had to do with the key joints. So we tightened that up as well. We found that we could do better if we were printing our timing pulleys rather than buying them and cutting keyways. Printing them gave us just more mechanical precision. So we shifted from purchase pulleys to printed pulleys. And what we were able to do is we're able to take 85% of the backlash out of our steering system. And by doing that, now we could drive freight. And we did this during the 2018 build season, because we saw that in 2018 game Power Up. Yeah, Power Up. Have to check. But you had those crazy autonomous routines in the beginning where you'd have to go out and go across the field and then score in the opposite side, and it really, the distances that you needed to travel in autonomous and be able to get to where you needed to be precisely were much greater than in the past, and we could not have done that without cleaning up the transmission and getting a Swerve robot that drives straight. It helps when humans are driving it as well, because in the past humans would just unconsciously make the corrections needed. Now they don't need to anymore, so driving's become easier, but the killer was autonomous. We just could not do autonomous really well until we solved that backlash problem. But now we have. Field-centric driving we talked about. Objective was make driving easier and really more intuitive for the driver. So in the past, the driver really had to put their brain into the chassis and understand what the orientation of the chassis is and where they needed to steer in order to get to where they needed to be. It's a little hard to do that. Personally, I am terrible at doing that. I never drive because of that. But it's become our normal drive mode since 2018, strangely enough, because again, a lot of things that we need to go around in that game as well. It makes driving by direct vision a lot easier. And in fact, the only time in this year's robot, the only time we're using robot-centric driving is during sandstorm, where you need to use a camera. So we use robot-centric during sandstorm. The rest of the game, we use field-centric. And our drivers love it. Left joystick controls the direction of movement, and it's all intuitive relative to the field. The right joystick then rotates the chassis. So again, really intuitive, really easy for the drivers to do. It's beginning to make Swerve driving something we don't need years of practice to get a competent driver for. We have software controlling the CVT. Basically, it's an automatic transmission. We're still working at improving those algorithms, but we try to keep on the maximum power curve of the motor. There was a lot of cultural change here too, because we actually developed field-centric a year before we used it, because our drivers were trained for robot-centric. They wouldn't drive with field-centric, so we had to make some personnel changes. And this is just a little bit of errata here. A lot of this is in our Swerve Central page on our wiki, and if it's not on the field-centric page, then there are links to where it is. We calibrate all modules identically relative to the module. That means I can put in a spare, I can change out a module, and I know it's calibrated correctly. They're not calibrated to the chassis, because if you do that, then the ones in the back are going to be backwards. They're calibrated to the module, and it's consistent, it's routine, it's documented. This is how you calibrate a Swerve module, and everyone does it the same way. It's really important. Another good thing for the wiki is that you can document these procedures. We hate set screws. I wanted to say that. Does anyone here like set screws? No? No? We organized the wiring harness on the Swerve because as we've added sensors to it, we found that we were getting more and more wires. Those sensors make the Swerve modules work more effectively, but what we found is that if you're swapping modules out in 2 or 3 minutes and swapping another module in 2 or 3 minutes, if you don't manage your wiring harness, things get caught and wires break. So it's really become part of the design, how we're going to manage that wiring harness. Where do the wires go when we swap a module? How do they get out? How do they go back in? How do they reconnect? And one thing about this is it's made us better designers. It's been challenging, but it's forced us to become better, to think things through a little bit further than we used, well, a lot further than we used to think through before. We plan tool access. How are you going to get the tools into where it needs to be? We used to use bolts and nuts to hold the pivots on until we realized it's really hard to get in to get that nut. So we switched to using rivet nuts because then the tool access becomes trivial. Really, for the team overall, our first design priority has been, and it continues to be, make things easy for the drive team. If you can change your design, change your software so that the drive team's job is easier, you should do that, because the drive team works really hard without you imposing extra missions on them. And then the second design priority is to make things easier for the pit crew, but we worry a little bit less about that. And that's all I have. If you have any questions.
Do you guys plan to use the new Falcon motors for your Swerve?
We have not tested the new Falcon motors. That's something we're really interested in. Right now, the new Swerve that we have, because the Falcons really just showed up on the doorstep, unexpected. What we have is we have Neos for the Swerve and the steering, but the Neos are crazy overpowered for steering. So the Falcons are, Gary, you want to add to that?
I think at this point, the team decided not to go with Falcons because they make the modularity of our Swerve modules a problem. You gotta change the CAN ID in your software if you change a module. And in the heat of competition, that's one more software step, one more place to make an error. So because the controller and the motor are all integral, the CAN problem is we're not going to use Falcons.
They're so similar. It's like...
They're so similar, and I think you're going to find as time goes on, the Falcons have a little thermal problem, and with our new design, we're worried about thermal heat dissipation. So we're not going to go with them at this time.
Where in your system is the steering encoder located? And I'm just trying to understand why backlash became such a huge issue relative to the steering encoder.
It's because it's not on the final stage. It's not on the final stage. It's on the steering motor shaft.
Okay.
So you've got the, you're measuring the angle on the steering motor, you've got a belt and pulleys before you get to the actual final stage. And also, so that should leave you okay with the gearbox in terms of knowing where you are, but not in terms of controlling where you are, because that still slips a lot. It became uncontrollable, so all of the backlash became a problem, even if it was part of the backlash you were measuring.
The control, the PID, has a hard time dealing with bad backlash.
Yeah.
Yes. When you guys use Neo, do you find the integrated encoder enough, or do you use a separate encoder?
We use a separate encoder. If you look at this, you see this little printed pulley down here. It runs off of another printed pulley on the drive pulley, and it drives an encoder on the opposite side of that plate. Because we have CVT, we wanted to actually measure the drive rotational speed, not the motor rotational speed, because they're not necessarily going to match. Peter?
Could you elaborate a little bit on how you do your calibration so that you ensure that they're all identical?
Yeah.
Or is that a trade secret?
No, it's not a trade secret. We have the orientation of the cage, the wheel, relative to the module. It's a fixed location, and we have pictures of it in that fixed location. We then just, we use clamps on our flex connector going to the rotational encoder.
Yep.
You can loosen the clamps, you can rotate the encoder shaft, and then make sure that you get that set to the minimum voltage, and then you reclamp it. Clamps, we hate set screws, but the clamp connections work a lot better and more reliably than set screws. We always use a, I didn't do that. We always use a flex connector between the steering drive shaft and the steering encoder, just to preserve the encoder.
Yep.
Encoders don't like
Yep.
rotational loads. Yes?
When you were training your new drive team, were there any specific issues that you ran into with like training them for Swerve drive?
Yeah, of course. But you want to know what they are, I'm sure.
Yeah.
Especially before we went to field Centric, not everyone can get their brain into the robot chassis so that they know which way they're going to have to steer. We would do a lot of testing where we'd spin the robot, and when the coach said, now go this way, and the driver would have to get out of the spin and go in the right direction. But not everyone can do that. And so you quickly whittle down your field of potential drivers to a few who can get their head into that chassis orientation. Now, it's easier with field centric. It's really opened it up to potential drivers, but I'd say that was the first thing, is how do you get people that can put their heads into that chassis where it can really be facing in any direction, moving in any other direction. How do you do that properly? Because it's hard. I can't. Yes?
Do you have any tips on switching from that like tank style and one directional movement to the field centric view in terms of like driver training?
Yeah, so when we started doing that, we ultimately had to change drivers, because the driver who was trained in getting their head into the chassis orientation couldn't change. But students get older and then they go on to other things. So, but we had to change drivers because then that was part of the cultural change. We developed a new drive mode, and we thought it was a lot better, but the drivers hated it initially, and they wouldn't use it. That's changed, but it's changed because there are new drivers who see that, yes, this is a lot easier. So it's changing. It's not just a technical change. A lot of times, if technical changes already fit into the way you do things, they're really easy to adopt. But when a technical change makes you change the way you do things, even if it's intrinsically better, it's hard for people to do that. That's why we've got a QWERTY keyboard on our computers. Yes, Peter?
What are you using for your gyro, for your field centric?
We're using the NavX.
It's working well.
Yeah, it really does. You've got some drift, but over the course of a match, it's not enough to be a problem.
And is it critical that it be centered at that point?
It's critical that we start the match aligned with the field.
With the physical location of the nav X, is it critical that it be in your center of rotation? Or
Uh,
handle the offsets?
It handles the offset.
Yeah, there is a cumulative error from not having it at the center of rotation, but it's not, I mean, the drift is probably the biggest, the cumulative error from being off center is not that bad.
But the turn arrow, or
It's, we're not off that much, and, yes, there is an accumulative error,
Right.
but it's not something we worry about.
Yeah, fortunately, FRC matches are relatively short. Yes.
Winning competitions is nice, but there's an underlying level of engineering thinking that's important for high school students to learn about risk minimization and making the optimal blend between solving problems in software or electronics or mechanism. When you're working with your team, do you ever try to make those issues clear to the students so they're not just thinking win-win, they're thinking about robotic design at sort of a higher level?
I think we try to do that, and I'm not sure we always articulate it as clearly as you just did. But yeah, I think that a lot of the changes we've made over the years, yes, it helps us win because things don't break so much, but it also it's just better design. And it provides you with a system that's going to work reliably and consistently.
And students who are going to become better engineers.
Yes, exactly.
Yeah, I'd like to say something like that. Swerve changed the mindset of our team. You cannot do Swerve and build all these other components unless your team becomes very project management oriented and you have a timeline, you have to become very disciplined. Okay, so once we took on Swerve, we became a much more disciplined team, and once you get that ingrained into your team over a couple of years, this spills over into all the other mechanisms in the robot, how you attack it, how you set up your project management, your timelines and all. It changed our team, because you can't do Swerve unless you change. You have to be very project management focused, or else you're going to have a drive base and nothing else.
But that also brings up the point, you know, Swerve is not magic from that standpoint. I mean, really challenging yourself to do, you know, stepping out of the box where you are into an area where, I mean, we could never do this before. If you're going to make that change in your objectives, you're gonna have to get better, or you'll just fail. Yes. Yes, you.
So in the picture that was on the board before it disappeared,
Yes.
there was a traction wheel for like the wheel you use in your module.
Yes.
Have you used Coulson's in the past?
Yes,
Or
we use Coulson's.
which do you prefer and why?
We prefer the traction wheel because it's light and cheap.
Do you find a difference in like actual traction of the wheel, like driving experience?
Not really. The Coulson's, we are very happy with the Coulson's, and then Eddie Mark came out with that, and it was light and cheap. We like both of those, light and cheap. They work well. We've been happy with the performance. They wear out, we change them. We have time for one more question.
With the field centric, you said that the starting point is relative to where it's put like on the field.
The orientation has to be fixed, so.
So after like the sandstorm or autonomous period, when it switches into the teleop, does that system just like stay? When we had it, that was our problem. We had it facing the right way and it's orientated the correct sandstorm, but once the teleop changed, we lose our like set position.
Okay, we don't lose our set position. It's set at the start of the game, and it's retained, even though we're not in field centric during sandstorm, the reference point on the gyro is already retained, and that we just have to make sure that when we set up the robot on the half, that it's aligned with the field. It doesn't need to be in a specific place, but it needs to be aligned with the field alignment.
Yeah, that's a software issue. We can address that. Listen, we have to wind up right now. Please give Clem a round of applause. Both the Swerve discussion and the discussion of how he has his team oriented or organized was very insightful, and you can take a lot from that. And thank you very much.